Okay, so in this video, we're going to go over the proper procedure for completing complete net ionic equations, as well as application of solubility rules when you are attempting to find a solid precipitate that is being formed in a chemical reaction. So first of all, in a double replacement reaction, okay, for a reaction to occur, there has to be some sort of driving force. We talked about the other day that there were some different things that could signal a chemical reaction was occurring. A color change, a mass change, the release of heat or light, the release of gas, which we said was often seen as bubbles going through a liquid. And then the last one we mentioned was the formation of a precipitate. So in some double replacement reactions, the force that drives the reaction is the formation of a precipitate. And without that precipitate being formed, the reaction simply does not occur. You just have your ions or your potentially reacting species just floating together in a beaker or test tube, not really doing anything. So we will be looking at primarily here a solid precipitate. So we determine whether or not a precipitate forms by using our solubility rules. For us, they are located on the reference packet. And so it's important to know the difference between what it means to be soluble and what it means to be insoluble. So to say something is soluble, it dissolves into ions in solution. So like sodium chloride or table salt is a great example of this. You put your table salt into water and it disappears. It dissolves. It breaks apart into its ions, which are too small for your naked eye to see. Something that is insoluble is something that does not dissolve in a solution. It remains together, or potentially, if it's a reaction occurring, comes together in that solution. And the way I kind of describe it is by saying, like, the two parts come together, they form the solid and kind of fall to the bottom of whatever container that they're in. And you can visibly see that solid at the bottom of the container. So on our reference packet, we have our list of solubility rules. We have things that are generally soluble in all quantities and all forms, and then things that are insoluble. That are generally going to be solid. And I say generally because to some extent, and sometimes that is a very, very small extent, everything is at least a tiny little bit soluble. Some things are just significantly more soluble than others. When we get to the section on equilibrium, we're going to actually talk about what's called KSP, which is the solubility product constant that governs how insoluble something actually is. And we'll find that a lot of things that we see here listed as insoluble are actually slightly soluble when you really look at it. But for the purposes of complete net ionic equation, we're going to go with what this says. So if you are on the soluble side, you will dissolve into your ions, and they will all be liquid or ion generating, except the exception. So if you come after an exception on this side, you will be solid. Anything before an exception is liquid. And then we see the opposite over here. On the insoluble side, all of those things are solid, except for the exceptions, which are liquids. So it's always going to be opposite. So we'll refer back to this list as we go through our examples. So there's two main types of problems that you'll be asked about your solubility rules. The first type is just to predict whether a precipitate forms in a reaction. It's kind of just saying, like, here are some reactants. Tell me what the products are and look them up. Is one of them a solid precipitate or neither of them a solid precipitate? Because your choice is going to be one or none. The other thing is complete net ionic equation, which gets a lot more into the details of what's going on in the reaction. So we're going to deal with this type first. This is kind of just the shorter hand version, and then we'll go through some complete net ionics. So our examples here, I'm going to try to get the examples and the solubility rules all on the screen at the same time. Will a precipitate form? So will a solid, remember precipitate is another way of saying solid, form in the following reactions? And if so, what is the precipitate? So I've given you 4 examples here. In these 4 examples, everything that you have been given are reactants. So before I can say whether or not a precipitate forms, I need to determine what my products will be. There's 2 ways you can do this. You can look at it, and if you're really proficient at your nomenclature, you can say what they are without having to write them down, look them up, and then just go to your answer. but some of you may need to write them both down, and that's fine. There's nothing wrong with that. So for the purposes of this video, I'm going to write both of them down. I think it's just a little bit easier to have them in front of you as you go look them up. So these are compounds and compounds. So what I have is the parts for a double replacement. So I know that the Fe is going to pair up with the Cl and the Ba is going to pair with the SO4 in my double replacement reaction. So the sulfate is -2. That makes the iron +2. So when I pair it with the chlorine, I'm going to have FeCl2 and I'm going to have BaSO4. And then I just need to look those up and see if either of them is solid. So I'll look up the iron 2 chloride first. All chlorides, bromides, and iodides are soluble on the soluble side, except silver, lead, and mercury. Well, that's iron. It's not one of the exceptions, so this is soluble. And I'm just going to cross it out. Now I'm going to look up my second product. This is a sulfate. All sulfates are soluble, except calcium, strontium, barium, mercury, lead 2, and silver. Well, that's barium. So that tells me that this is my solid. So I can circle it like I've done here. I can write yes and the identity of the solid precipitate. Either way, you just need to be clear. What is my answer? All right. So let's look at number 2. NaOH and MgCl2. So we know that the Na is going to go with the Cl, the Mg is going to go with the OH. That's going to give me NaCl plus MgOH2 as my products. So hopefully at this point in life, you know that this is salt and you know what salt does in water. It dissolves. We can reinforce that by looking at our solubility rules. All chlorides, bromides, and iodides are soluble except silver, lead, mercury. That's sodium. It's not an exception, therefore it is soluble. Then I'm going to look up my magnesium hydroxide. All hydroxides are insoluble except group 1A, strontium, barium, and ammonia. Well, magnesium is not in group 1A, and it's none of our 3 named exceptions. So this guy is our solid. All right. So let's look at our next one. NaNO3 and KC2H3O2. So I know that the Na is going to go with the acetate and the K is going to go with the nitrate. So that's going to give me NaC2H3O2 plus KNO3. So I'm going to look at my acetate first. All nitrates, acetates, ammonias, and group 1A salts are soluble. There are no exceptions here. So that is soluble. And also, I already read this one. This is a nitrate. All nitrates are also soluble. So I don't have a solid here. I could write these both, cross them out, or I could just write no. Okay. And then my last example. So I've got silver nitrate and sodium chloride, which will produce silver chloride and sodium nitrate. And I just read the rules about nitrates, so I can already tell this is going to be soluble. So let's look at my chlorides. All chlorides, bromides, and iodides are soluble except silver. Well, there's my exception. So this is a solid. Okay. This same idea is going to follow us into our complete and net ionic equations in terms of it being the first step that we have to do when we determine if there is a solid. So let's look at procedure and some examples for how to write those complete net ionic equations correctly. If I could turn my page, that would be great. All right, so let's go through some steps. Steps to write a complete net ionic equation. First, if the products are not given, predict the products and balance. Sometimes they're given, sometimes they're not. Sometimes you just have reactants and you have to do what we just did and predict the products. Always, if the products are given, always double check to make sure that it's balanced. That is something I've been known to do, is give you products but not balance the equation. And if you just go on autopilot and you don't check to see if it's balanced, you end up writing your complete net ionic equation wrong because you don't have appropriate coefficients. So always check for balancing. Then look at your products. Check your products for a solid. Look for an insoluble precipitate. Your options are going to be, you're either going to have 2 soluble compounds or 1 soluble and 1 insoluble. You're not going to get a situation where you have 2 solids formed. If you think that that's where you're at, go back and check what you predicted for your products because you probably have done something incorrectly. All right, then once you have identified the solid, you disassemble everything into its ions with charges. Remember, ions have charges, except for the solid, because once the solid forms, it stays together. So everything except for that. Subscripts from the drop and swap become coefficients. So if you have a subscript on a single element, like calcium with a subscript of a 2, then it's going to become 2 as a coefficient on the calcium. But if you have a subscript that's there as part of a polyatomic, that stays where it's at. Okay. If you also have a coefficient and a subscript, then the coefficient and the subscript are going to multiply. So if I had, just as an example, like 3Ca3PO4 2, then I would have 9 calcium, because 3 times 3 is 9. All right. Cross out all of your spectator ions. Spectator ions are things that are not involved in the formation of the solid. They are spectating. They are watching. And then whatever is left is the net ionic equation. That's what's actually occurring. When we say something is net, that's what the change is. And the change is the individual particles coming together to make that solid. All right. If a solid is not present in step 2, right, then no reaction is occurring and the remaining steps are not necessary. So let's look at our first example. So first example, AgNO3 plus H2SO4, I gave you reactants. We have to predict products. So just like we've done before, I know that I'm going to take my positive ions and flip-flop what they're paired with. So the H will go with the NO3, the Ag will go with the SO4. So Ag I know is +1, SO4 is -2, so this is Ag2SO4. And H +1, NO3 -1, HNO3. So those are my products. I need to balance my equation. So I have 2 silvers here. I'm going to place a 2 there. That's going to give me 2 nitrates. So I need a 2 there. I have 2 hydrogens, 2 hydrogens. All right, so we're good. We're balanced. Remember that this is a complete balanced chemical equation. There should not be any charges in my top line. There will be charges in the complete ionic and the net ionic, but in the first line, where I'm predicting and balancing, there should be no charges. All right. So now, step 2, check the products to see if I have a solid. Well, I already know that this is a nitrate. Nitrates are never solid. So I'm just going to check the sulfate. So all sulfates are soluble, except calcium, strontium, barium, mercury, lead, 2, and silver. Well, this is silver sulfate, so this is my solid. So now I'm going to take apart everything into its ions with the exception of this solid. All right. So I have a coefficient here. That means that coefficient applies to both parts. So I'm going to have 2 Ag +1 plus 2 NO3 -1 plus I have a subscript on the H. It's a single element. It's not a diatomic. It's there for a drop and swap. So I have 2H plus the SO4. Remember, that is the polyatomic. So that goes together. SO4 -2, arrow. My solid stays together. Plus 2H plus 2NO3 minus. Then I'm going to cross out everything that's not part of my solid here. So the easiest way I found to do that, start on the product side, cross off everything on the product side that's not the solid, and then the same matching parts on the other side. Those are my spectator ions I've just gotten rid of. And everything that's left is my net ionic equation. 2Ag +1 plus SO4 -2 yields Ag2SO4 solid. So things to make sure that you watch out for: no charges in the top line, must be balanced, must mark the solid with an S. In my second line, I should have charges on everything except for the solid. Solid should still be marked with an S. Third line, I should have charges on the left, no charges on the right, solid still marked with an S. Okay. All right, let's look at our next example. So same thing, we have reactants, we need to predict some products. So zinc is going to go with my phosphate, and my sodium is going to go with my nitrate. So that's going to give me Zn3PO4 2 plus NaNO3. then I need to balance. So let's see, I've got 3 zinc, so we'll go with a 3 here. 2 phosphate, so put a 2 here. That's going to give me 6 nitrate and 6 sodium, so 6 there. Okay. All right. We know already no nitrates are ever solid, so let's just look at our phosphate. All carbonates and phosphates are insoluble except group 1, and zinc's not in group 1, and ammonia, and zinc's not ammonia. So this is my solid. So now I'm going to take everything apart into its ions, and that's going to give me 3 Zn plus 2 plus, so this 3 and that 2 is going to give me 6 NO3 minus 1 plus 2 times 3, 6 Na plus 1 plus 2 PO4 minus 3 yields Zn3 PO4 2 solid plus 6 Na plus 1 plus 6 NO3 minus 1. Crossing out everything that's not a part of the solid, so the 6 NO3, the 6 Na, the 6 Na, the 6 NO3, and then now I write what's left. 3 Zn plus 2 plus 2 PO4 minus 3 yields Zn3PO4 2 solid. So kind of big picture, think about what's occurring. If you look at the complete, you've got 4 things all bouncing around together. When you look at the net, I only have 2. What that's telling me is that even though I have 4 things, only these 2 are reacting. These 2 are a part of the reaction to make the solid. What's happening with the other ions? They have not changed in my reaction. They were the same on the reactant side, now they're the same on the product side. They're not doing anything. They're not involved in the reaction. That's why we call them spectator ions, because they're just watching. They're not doing anything. All right, so we're going to look at 2 more. So again, first step, predict my products, KOH and SnNO3. So K is going to go with the NO3. So KNO3 plus, the tin looks like it must be plus 2 because nitrate's minus 1 and I have 2 of them. So SnOH2. All right, for balancing, I have 2 OHs, so I'm going to place a 2 here. And what else? 2 Ks and 2 NO3s, so a 2 there. All right, all nitrates are soluble, so I can skip that one. Let's look at our hydroxides. All hydroxides are insoluble except group 1A, strontium, barium, and ammonia. This is tin, so yeah, we should be good. This is a solid. All right, now start taking apart. 2K plus 1 plus 2OH minus 1 plus Sn plus 2 plus 2NO3 minus 1 yields 2K plus 1 plus 2NO3 minus 1 plus SnOH2 solid. Getting rid of my spectator ions, the things that are not reacting. That leaves me with 2OH minus 1 plus Sn plus 2 yields SnOH in parentheses 2. All right, and our last example. So rubidium fluoride and hydrogen monochloride. Predict my products. Rubidium is going to go with chlorine, so RbCl, and hydrogen is going to go with fluorine, HF. So let's look at my products. So all chlorides, bromides, and iodides are soluble except silver, lead, and mercury. Well, that's rubidium. That's not an exception, so this is soluble. Now I need to find my fluorides. All fluorides are soluble except group 2, well, hydrogen's in group 1, lead, and iron. So this is also soluble. So because these are both soluble, I don't need to write a complete or a net because no reaction, RXN, remember, is reaction, is occurring because everything is soluble. Okay? All right, so that should get you through your complete net ionic equations.